If you ever thought about designing your own PCBs at home to maybe shrink a project down, or so you don't have to solder as many wires together, you've come to the right place. In this video, I'll show you how to design and assemble your own circuit boards at home without any special tools. To make the process easier to understand, I'll be using a very simple and popular IC, the TP4056. It's a battery charger IC, and if you ever built an electronics project with a battery before, you probably heard about it. PCB design is an art of its own, and it can get very complicated. It would be impossible to cover everything in a single YouTube video, so take this video more as a cheat sheet, which will help you get into this world by showing you the basic steps. This video was sponsored by NextPCB. I wanted to make this video for quite some time now, and when NextPCB reached out, I was really excited. They offer PCB manufacturing services, PCB assembly, and you can order your SMD components directly from them as well. You can use their Gerber viewer to check your boards, and you can see the quality of the PCBs for yourself, as NextPCB supplied the boards for this video. Before we can design a PCB, we need an actual idea to work around. It could be a simple breakout board like the one in my electric skateboard remote, and this is the most simple example I can give you. It's the Firefly remote controller project, and originally you would secure an Arduino Nano board inside and solder the wires together. There is a lot to solder, and I wanted to make mine look a little bit nicer, so I designed a simple board to hold everything together. In this case, you would draw a schematic, assign a footprint to each component, route the traces, and order the boards. It's an easy way to start drawing your own boards since there are no complex circuits, long datasheets, and small components. As I said in the beginning, in this video I'll be designing a board around the TP4056 IC. It's a battery charger IC which takes 5 volts on the input and charges a 1-cell lithium-ion battery on the output. There are 2 LED indicators letting you know when the battery is charging and when it's fully charged. You can see that it doesn't require many components, so it's a perfect IC to start your first project with. I'll be designing 3 different boards. Whenever you start working with a new IC, it's always a good practice to first make a bit larger board, with as many breakout points as possible. It's much easier to fix problems later that way, and you can test multiple IC configurations since there's enough space to easily make changes. My favorite thing to do when designing boards is to try to make the board as small as possible, so that's the next thing I'll be doing. This is the worst thing to have when you need to troubleshoot something, so I wouldn't recommend doing this until you verify your design on a first prototype. The first board is clearly for a development phase, the other one is just for fun, but now let's actually create something useful. I decided to go with a 4-way 18650 battery charger. It has a USB Type-C connector on the input, 4 ICs for 4 batteries, LED indicators, and the battery holders. And those are the 3 PCBs I'll be designing and assembling in this video. At this point we have the idea figured out, and the next step would be to choose an IC and to take a look at its datasheet. I decided to go with the TP4056 IC even before starting this video, so I don't have to do this part of the research. Even though I don't have to find an IC for my project, I'll show you how to source one for yourself. First example would be a simple 3.3 volt regulator. You can use DigiKey, Mouser, LCSC, or in worst case AliExpress. AliExpress is useful when you're fixing something and when you already know the part number of the IC you're looking for. If the IC you're looking for can be found on any of the other sites, AliExpress may be a good place to check. LCSC is usually the cheapest option, and I always check it first. Let's go to lcsc.com and type 3.3 volt LDO. Then we can click on one of the regulators and check in which category it is. It's under linear voltage regulators, and by clicking on the category, we can see all of the ICs they can supply. It's almost 60,000. Now you can really get into details by filtering the search results. I'd like an input voltage of up to 15 volts, output type is fixed, output voltage of 3.3 volts, and the maximum output current of 1 amp. Before applying the filters, I like to check the in-stock option and then click apply. Now we can sort the regulators by size or price, and I'll take a look at the LD1117AG. By quickly going over the datasheet, we can see that it is what I was looking for, and the price of a single IC is only 7 cents. This was a simple example using a voltage regulator. You can find Atmel and STM chips, MOSFETs, diodes, resistors, capacitors, and everything else you may be looking for. Now let's try to find the IC I'll be using in this video. I'll go into power management ICs and battery management ICs. I'll set number of cells to 1, maximum charge current to 1 amp, check in stock and apply the filters. And here it is, the TP4056 IC. After choosing an IC, the next step is to deep dive into the datasheet. Luckily, the TP4056 is a very simple IC to design around, so this won't take too long. After you find your IC on a website of one of the suppliers, there will be a datasheet provided in most cases. When sourcing components on LCSC though, some datasheets will be written in Chinese, which may give you some trouble. Luckily, datasheets are really easy to find, so if you do end up with a Chinese one, try googling for an English version. The first page always gives you the general information about the IC, what it is, what it's meant to be used as, and the main features like programmable charge current in this case, or the maximum input voltage. Next thing you may want to look at is the pinout of the IC. My IC lives in a SOP 8 footprint, meaning it has 8 pins. You can check the detailed dimensions of your footprint by googling for your footprint dimensions. Each pin has a special function and needs to be connected as stated in the datasheet. We can take a look at the detailed pin description below. Take your time and go through each pin a couple of times to really make sure that all of your connections are correct. You can always try to find some development boards, or even better, some other people who made similar projects with it. The temp pin can be used to connect an external temperature sensor. If the temp pin voltage is below 45% or above 80% of the supply voltage on the input for more than 0.15 seconds, charging will be suspended. We can also bypass this function by simply connecting this pin to ground. RPROG pin is used for setting the battery charge current. A formula for calculating the resistor values is provided, but there is also a table at the end of the document which states the recommended resistor values for different charge currents. Ground pin simply connects to ground, VCC pin is the positive voltage input for powering the IC, and the BAT pin connects to your battery. Now let's quickly go over the two LED indicators which will let us know when the battery is charging and when it's fully charged. While describing these pins, I'll use a couple of terms like a pin being pulled low and a pin being in high impedance mode. A pin being pulled low simply means that the pin we are talking about is connected to ground through the IC itself. We will use this ground path to power a small LED. The other state is a pin being left in high impedance mode. It simply means that the pin is not connected anywhere. With our configuration, when a pin is being pulled low, an LED connected to it will shine, and when the pin is in high impedance mode, the LED will stay dark and turned off. Looking at the pin description, the datasheet says that the charge pin number 7 is pulled low while the battery is being charged, and when the battery charging stops, the pin will be in high impedance mode. Standby pin number 6 will, on the other hand, be pulled low while the battery is not charging and will be in high impedance mode while the battery is being charged. CE pin is the chip enable pin. Pulling this pin high will turn on the IC, while pulling it low will put the IC into disabled mode. If you wanted to use an on-off switch, this would be a perfect place to connect it to. Under all of this, you will find an LED indicator table. We already went over the charging status indicators, but there is some extra information here as well. If the input voltage is too low, or if the temperature is out of range, or if the battery is not connected at all, none of the LEDs will shine. On the right, there's a table with recommended RPROG values. On the left of the table is the RPROG resistor's resistance in kiloohms, and on the right is the battery charge current in milliamps. 1 kiloohm is 1000 ohms, and 1 milliamp is 0.001 amps. I'd like my battery to charge with a current of 1 amp, so I'll go with a 1.2k resistor for a charge current of 1000 milliamps. And the last and most interesting thing, the schematic. You can see how everything is connected here, but don't fully rely on these, since they're incomplete most of the times. It will help you to get a better picture of how everything may look in the end, but pin description is definitely more important. If you ever do get stuck, you can always Google around and find other similar projects or development boards with the same IC. And that's it, only 3 pages. Datasheets usually have hundreds of pages with different schematics, charts, footprint dimensions, pin descriptions, packing information, and much more. Now you can see why this was the perfect IC for a first YouTube video project. After doing all of this research, it's finally time to start drawing your own schematic. And to do that, you will need a PCB Design software. Some of the options are EasyEDA, KiCad, Eagle, Altium Designer, etc. There is a lot of options to choose from, and if you're not sure which one to pick, I think Altium and KiCad should be your best 2 options. KiCad is great because it's open source and free. A lot of people use it, and most of the PCB projects around the internet are made in KiCad, so it's easy to find interesting project files and modify them to your needs. Altium Designer is focused more at businesses and the professional side, like automotive industry for example. It is the PCB software used by large companies, and it is the more powerful one. It comes with a steep learning curve and price, so at this part of your journey, KiCad should be the easier and faster approach. I started designing in Altium a few years back while watching some tutorials on Udemy by Robert Feranec. His Fedevel Academy is the best way to start learning PCB design in great detail, and I'll leave his YouTube channel linked down below. This video is already almost 10 minutes long, and you haven't even seen me route a single board, so as I said at the beginning, take this video more as a cheat sheet which will show you all of the basic steps. I will not turn this video into a 24-hour Altium Designer tutorial, since if you're interested in that, you can easily find one on Udemy or some other similar site. And after bombarding you with random information for 10 minutes straight, it's finally time to actually do something. With your CAD software of choice opened, let's create a new schematic document and import our IC. I will keep the datasheet opened on the other side of my screen, and I'll start with the most basic connections first. The VCC pin is used for powering the IC, and we will power it via USB Type-C connector. VBus pin on the USB connector is voltage high, so I'll connect this pin to our VCC pin on the IC. The datasheet says it's a good practice to place a 0.4 ohm resistor in series between the IC and the USB connector, so I'll do that too. Before continuing with the rest, there is one thing we must not forget when designing around Type-C connectors. USB Type-C supports lots of different protocols, and if you were to connect a smart PD brick to this circuit, nothing would happen, because the charger wouldn't know what voltage to output. To simply solve this problem, we can place two 5.1K pull-down resistors on the CC lines of the connector. Ground and MH pins can be connected to ground, so I'll do that now and we are finished with the USB side. Next thing is the CE pin, short for chip enable. Datasheet says the IC will be in working mode while this pin is pulled high, so I'll simply connect it to VCC. Charge and standby pins are used for LED indicators, so I'll place two 0603 LEDs with series resistors. Two ground pins on the bottom connect to ground, and the next pin is RProg. We can calculate the resistor value ourselves or simply take one from the provided table in the datasheet. I want a charge current of 1 amp, so I'll place a 1.2K resistor between the pin and the ground. I don't want to use temperature functions, and the datasheet said that we can disable them by simply connecting this pin to ground. And the last one, the BAT pin. This one connects to a battery positive, and we can create some solder pads to make that easier. And all of the connections are complete, but there's just one more thing we need to add, and that's the coupling capacitors. I will put one 100 nanofarad and one 10 microfarad on the input side, and one 10 microfarad on the battery side. We can also add one LED that will let us know when the device is powered on. All components I'm using are 0402 or larger in size, and after the boards are done, I'll show you how to export a bill of materials and order everything. For this video I did prepare 3 different boards, and all of them have a little bit different schematic, so I'd like to show you that before moving to the PCB design. The 3 boards are the tiny one, the development board, and the 4-way 18650 charger. Let's start by looking at the dev board first, because this schematic is built to be bulletproof by enabling you to change all of the major connections after assembling the board by simply moving some 0 ohm resistors around. The first example is how I connected the enable pin. You can see that it is connected to VCC or ground simply by moving this resistor to the on or off position. Another major change is that now you can use the temperature functions if you wanted to. If not, place a 0 ohm resistor to the off side. The whole board is a bit larger, and the last thing I see that is different is that I added some solder pads to the input too to make it easy to solder some wires on the input if you decided to power it that way. The tiny board follows the same schematic but with as little components as possible. The main thing I did is placing this 2-in-1 LED IC, which has both red and blue LEDs inside, while taking space of just a single 0603 LED. Everything is more compact, and I removed as much silkscreen as possible so I can move the components closer to one another. The 4-way 18650 charger board is just copy-paste 3 more times. The only major change is that instead of the solder pads on the output of each IC, I added 4 18650 battery holders. On the board you can see that it literally is just a copy-paste of a single board done on a larger scale. All of the ICs are powered with the same USB connector, and each output has its own battery slot. The schematics are done, and in the following chapter I'll show you how these boards were routed using a simple example board. But before doing that, I'd like to quickly show you the main differences between the 3 boards I designed. The first one is the dev board. The USB connections remain the same as before. Power supply has its own LED indicator, there's a 0.4 ohm resistor on VCC, and basically everything else is the same too. The main difference is that I added some breakout points and 0 ohm resistors that can be used, for example, to switch the CE pin from ground to VCC. The small board follows the same idea with only difference in the LED indicators. This time I used a 2-in-1 LED chip to save space on the board, and I got rid of extra resistors that were not needed. The 4-in-1 board is the most complex one, but again follows the same idea and same schematic. There are 4 ICs this time, 1 for each battery, USB is the same, pads are the same, and the only difference is that this time I added 18650 battery holders on the outputs instead of the battery pads like before. And we finally made it to the PCB design chapter. This video did turn out a lot longer than I was hoping for, so thank you a lot for watching through the whole thing. After completing your schematic, it's time to draw your PCB, and this is my usual workflow in Altium. The first thing I do is import all components from the schematic and delete the rooms and the designators. Then I turn on split view and enable cross probe. This tool now highlights any component I select in the schematic on the PCB too. It's always recommended to do PCB layout before routing any traces, and this will help you get a better idea of which shape your board may take. I'll group the components close to the IC and rotate them as necessary. When doing your connections, you first focus on the signals, then power and ground at the end. Another cool trick is to hide ground and power connections, so it's easier to visualize how the signal traces may look. This is a pretty simple board, and you don't have to worry about signal integrity or anything similar yet. You can place the components however you want, but the only thing I would recommend is to place the capacitors as close to the pins as possible. The 10 microfarad cap on the input should be as close as possible to the input power side. That is your VBus pin on the USB connector. The 10 nanofarad cap should be as close as possible to the IC VCC pin. Then on the output, to make the whole board resonate as little as possible, place the 10 microfarad cap as close to the bed pin as possible, since this side is switching and we want to eliminate the noise as close to the source as possible. When you have your layout sorted, you can draw your board shape or import a DXF file from another CAD software. By selecting the outline and clicking on Define Board Shape, we got the PCB shape we were looking for. It would be a good idea to enter some PCB design rules before routing any traces. The rules specify the minimum and maximum parameters like trace size and spacing of the components. This information can be found on PCB manufacturing sites on the capabilities section. The next thing is to create a basic stackup and set the board thickness to your preferences. I'll go with a standard 1.6mm PCB thickness, which is a standard in most cases. For routing signals, I keep my trace width to 0.254mm, which is 10 mils. 1 mil is 1/1000th of an inch, and it is the standard measurement unit used in PCB Design. Us guys from Europe though still like the metric system more, so you'll have to watch me use millimeters in this one. Two pull-up resistors get connected to the CC lines, the AirProg resistor goes to the AirProg pin, the LED resistors connect in series with the LEDs, and the capacitors are connected as I explained earlier. When all of our signals are routed, the next thing is to connect the power. Since I don't have much space left on this side of the board, I'll use some bias to move my connections on the other side. I'll connect the two VBus pads together with a large polygon, and then the VCC net gets connected to the 0.4 ohm resistor. And now two pins are getting connected here, the CE pin and the bed pin. The CE pin needs just the signal, so I'll connect it to the VCC rail, which is the same as on all of the other signals on the board. The VCC pad on the other hand will draw lots of current, so I'll connect it with a polygon instead. If you're not sure how thick your traces need to be, you can calculate them using an online trace width calculator. Another polygon will connect the battery pad and the bed pin of the IC, and at this point all signals and power rails are connected, and the only thing left is to connect the ground. Let's pour two ground polygons on both sides of the PCB and connect them together with an operation called via stitching. In most cases this does connect all grounds together, but you can add more vias if something gets missed. One more thing I like to do is to add teardrops to my traces, and of course then the vias. Now we can run a design rule check and fix any issues if present. If not, double check everything one more time, and when you're sure that everything is correct, we can export the files and order our boards and components. To order the PCBs we just designed, you will need to export Gerber files first. Every CAD software is different, but in Altium, I open the output job document, and under fabrication outputs, I create my Gerber files and NC drill files. After exporting, we are left with two folders named Gerber and NC drill. Now add both of these to an archive, and this is your Gerber file for the PCB you just exported. The next step is to check if everything is correct. For checking Gerbers, I like to use a free piece of software called ViewMate. Go to File, Import Zip, select your Gerber file and click OK. Now we can go through each layer and make sure everything is right. I'll turn off all of the layers first and turn on the top copper layer. Now we can enable the top solder layer to see which parts of the board will have exposed copper. The next one is the paste layer, and this one is used to create stencils for applying solder paste, which are used while assembling our PCBs. My output pads, for example, don't need solder paste, so now I can double check if I removed the paste layer from them earlier. The last one is the overlay layer, and this is simply our text and ink. Now you can check all of this on the bottom layers too, and then we have our board outline, which looks okay to me, and the last two are the holes and slots. If you didn't find any issues after checking the file, we can finally order our boards, and for this I will use Next PCB, the sponsor of this video. On Next PCB site, let's go to PCB quote and upload our Gerber files. After analyzing is done, we can use their Gerber viewer to check the board one last time. Some of these settings got selected automatically after uploading the Gerbers, but you must always go through each setting and make sure everything is selected right. I did make a huge mistake while making this video, and I did it by simply going through these settings a little bit too fast. Our layer count is 2 and we do not have different designs on this board. Size looks to be correct, and for the quantity, I'll leave it at 5 pieces. The larger your quantity is, the cheaper a single board gets. Board type is single piece, and I didn't design any breakaway rails. For PCB thickness, I'll go with a standard 1.6mm, and I really like black and white boards, but they do cost a little bit more, so we can leave the color to green. Silk screen is your text, and then set outer copper weight to 1 ounce, tray spacing can be left at 5mm, and minimum drill at 0.2mm. If you want your wires to be covered like this and not exposed like this, make sure you select tented vias. The surface finish is how your pads will turn out. Anning looks really nice but costs a lot, so I'll leave it at standard, which will be just fine for this small board. Now you can select a couple of more settings, but for this simple project you can leave everything same as mine. After all of that, if you choose to get a stencil too, the first thing to look out is the border type. This is how a normal hobby use stencil looks like, and this is how a huge stencil for a huge stencil printer looks like. You definitely want the small one, so select non-framework. In our case, it will be a stencil for solder paste, and with stencils, I like to keep them at the same size of 150 by 150mm. This is a single side board, so we'll need a single stencil of the top side of the board. Quantity is 1, and the rest of the settings can be left as they are. Now select your build time and shipping, but note that the price of a single PCB design can get drastically cheaper if you decide to go with larger quantities. In this case, I would pay something like $3 for 45 extra PCBs. Enter your email or login and add the boards to your cart, and that's it. The boards are now on the way, and the next thing we need are the components, so let's quickly go back to Altium to generate a BOM file. Let's go back to the job output file, and under report outputs, I'll select bill of materials and open the settings. Under columns, I'll disable libref and enable manufacturer part number. File format I want is CSV, and after that I'll export the BOM. Inside Google Sheets or Excel, you can import it, and here you can see all of the required components that are needed to build the board. You can use DigiKey, Mouser, LCSC, etc. But if you don't feel like spending any more extra time, Next PCB has a BOM service as well. You simply upload your CSV formatted to their template and they handle the rest. And then if you don't even feel like building the boards yourself, or if you're not confident working with such small components, they offer PCB assembly services too. The boards are ordered and so are the parts. Now we wait, and when everything arrives, we can finally assemble the boards and test them out. And with all components, PCBs and stencils on the desk, we can finally assemble the boards and see how they work. To proceed, you will need some tools, and the most important are the tweezers. You need a really fine tip, specially designed for electronics. The one I have are holding up really good and are not expensive, so I'll make sure to leave a link down below. So, tweezers, a box cutter, maybe some pliers, tape, etc. Nothing special. A microscope will come in handy, but if you don't have one, you can use larger components to make the assembly process easier. I will use my microscope so I can film what's going on, and overall my pick and place accuracy goes way up when I use one, so that's a plus. The next thing you'll need is solder paste. A low temperature one will be easier to work with, and I got mine from AliExpress. Solder paste isn't something you should cheap out on, but even though this one was really cheap, the boards turned out really nice in the end. I'll try to link as much stuff down below, so if you're looking for something I used in the video, make sure to check the description. The assembly process goes like this. You sort the components and prepare everything. Clean the boards with alcohol, apply the solder paste with the stencil, pick and place the components, and bake the boards so the solder melts and solders everything together. To heat the board, we usually use special PCB ovens, but since this is a single side board, a small hot plate would be a perfect tool to do so. Since I don't have a hot plate, I'll try to solder mine with a hot air station. So, the first step. let's prepare everything. I'll show you how I assemble the dev board and then I'll do the rest in a time lapse or something. I'll open active BOM inside Altium and go through each component once the solder paste is on the board. Applying solder paste without a stencil printer can be a bit tricky and I'm really not used to it, but I did try my best. I am a bit spoiled since I always had a stencil printer nearby and this was actually my first time building a solder paste jig out of scrap boards. I didn't watch any tutorials, but I sort of built something I remember from watching other videos back in the day. Make sure to secure everything really good, and when you put the stencil over the board, secure it with tape on all sides so it can't rotate. Since I never did this before, it did take me a couple of times to apply the paste right, but in the end it turned out pretty fine. First, I wanted to apply the paste directly to the stencil, but that didn't work. What did work was to apply a small amount of paste on a separate plate and mix it well. Then I transferred some to the stencil and used an NFC card as a squeegee to apply it. If you want the paste to be as clean as possible, try to apply it in one go. With the paste applied, I gave it a little QC under the scope, and now I can start stuffing the board. I'll keep the board opened in Altium together with the active BOM, so I know which components go where and which ones are already placed. Take your time to place each component in its place correctly, so you don't have to rework the board later. Here you can see that it's a lot easier to place 0603 components instead of 0402. So if you really don't have a microscope, you can use 0603 or even larger components, which are much easier to pick and place. I like to place smaller components first, then the IC and the USB connector last. It's much harder to place small components when you have to worry about larger ones that are already on the board. After all components are on the board, double check everything, and then finally I'll try to solder everything together. This low temp paste melts at around 140 degrees Celsius, so I'll hit the whole board with 200 degrees Celsius set on my heat gun, with a low fan speed so it doesn't blow away any components. Really important thing is to not melt any of the plastic components like the lenses of the LEDs, but still make sure that the solder joints are good. I found that a temperature of 200 degrees Celsius made really good solder joints and it didn't damage anything. While heating up the board, make sure it's not sitting on something like aluminium that will just draw the heat away. Mine was, so I decided to place a piece of stencil packaging under the PCB while heating it up. After soldering is done, I'll clean the desk and inspect the board under the microscope. If you see any solder ridges or components which are not soldered right, now is the time to fix them. To be honest, I was really surprised how the board turned out. It's really clean and all connections look really good. I was expecting a lot worse results since I don't have all the equipment and the paste I used was very cheap. Overall, I call this a big success. After confirming everything looks good, the next step is to test the boards, which I'll show you in the next and the last chapter. I still have 2 more boards to assemble, so I'll keep quiet for some time until all 3 boards are done. The boards are assembled, so I can finally test them out. I'll start with the dev board, and the first thing I'll try is to connect 5 volts to the input pads. I'll set my lab bench power supply to 5 volts and limit the current to around 100 milliamps to protect the circuit if something goes wrong. Red goes to 5 volts in and black to ground. The first good sign is that there is no smoke and the power LED is shining, letting us know that the power supply is good. Without a battery connected, the standby LED is shining, which is a bit different from what the datasheet said, but these chips are produced massively by lots of different companies, so unless you go with a legit brand, such details won't always match. The next crucial thing I want to check is the output voltage, which is jumping from 4.2 to 4.3 volts without any load, which should be fine. Let's connect a battery and see what happens with the LEDs and the input current. Standby current is out and the charge LED is now shining. Input current went up and so the battery must be charging. Let's check what current we have going to the battery. This battery is almost empty and the charge current is just under 1 amp, which is awesome. Next step is to leave the battery to fully charge and see at what voltage it stops. After about an hour, the battery is charged and the charger stopped at just around 4.2 volts. All main functions are working flawlessly, and now there's just one more thing to test out, and that's the USB port. I'll connect it to a non-PD power supply first to see if all 5V rails are connected right and if they are working as intended. Everything appears to be working same as before, so that's alright. The final test is to see if we are activating 5V PD correctly. I'll connect my Type-C to C cable to the PD port of my power supply, and if the CC lines are configured correctly, we should have 5V on the output of the power supply. The final test has passed, so I can officially call this whole project a big success. Now let's try the small one, connecting a USB cable for power and a small battery to test the LEDs. And perfect, it works. The 4-way charger gets the power the same way, but this time I need some 18650 cells. Each slot appears to be working, and that's so awesome to see. All 3 boards have passed all of my tests and are working exactly as I wanted them to. And here we are at the end of the video. After nerding the shit out of you for 30 minutes straight, you are still here. I really hope you enjoyed this video same as I enjoyed building these PCBs. This video took me months to make, so I really hope you are going to enjoy it. I tried to cover as much stuff as I could to make the whole process as clear as possible to someone who is just starting out. As I said at the beginning of the video, this wasn't meant to replace a whole course because that would take a lot of time. A lot of details were kept out, but if you really want to start drawing your boards, now you have the knowledge of what's required and you're ready to jump in such a course to learn all the details. If you decide to go that way, I'd like to recommend you this course by Robert Feranec. That's the same one I watched while starting out, and it helped me understand all of the basics. I'll try to link all the tools, components and accessories I used in the description, and if you decide to get something, make sure to use my links because they help me fund future projects on the channel. They don't add any cost to you, but I receive a small percentage from your order. If you enjoyed the music in this video, it's actually all made by my friend Danny, and I'll leave his Patreon in the description if you want to check it out. The project files are not ready yet, but will be available soon, and I'll leave a pinned comment when they are ready. Thank you Next PCB for sponsoring this video, and thank you all so much for sticking to the end. I hope to see you in the next one very soon.